All right, here's going to be hopefully the last video on DFTs, and then we're going to move on to continuous time. So if you're getting bored of DFTs, great, because it's the last video. We're going to talk about three properties here. Let's first go over the three properties. Property one is that if my signal xn is entirely real, then its DFT is conjugate symmetric. What does that mean? Well, that means that x of, what's the best way to put this? X of minus k is the same as x of k, except we have to conjugate one of them. Conjugate either of them, it's the same. Okay, so if my signal x of n is real, then its DFT has this property. Question, why do we care? Well, let's recall, first of all, that DFT is periodic. The DFT itself is periodic, which means x of k is the same as x of k plus n. Okay? In other words, let me write out all the possible frequencies we could. Remember, k can be anything from negative infinity to infinity. So we could go all the way from negative infinity. We could come into, let's think, what's the way I want to write this? Yeah, we could come into negative n over 2 plus 1, and then all the way into, negative 1, 0, 1, to n over 2, continue up to n, and then continue all the way up to infinity. So here I just listed out the frequencies. I've highlighted some specific ones, but here are all the possible frequencies. As soon as we see this property, what can we do? Well, this tells us we only need to keep n of them. It doesn't matter which n. If I keep these n, then let's say I wanted the next one, n plus 1, well, that would be the same as 1, right? If I wanted, n plus 2, well, that would be the same as 2. So I really only need to keep n frequencies. So technically, actually, I only need to keep 0 to n minus 1, not n, but not a big deal. I want n frequencies. Okay, great. Now, that's great. So we could keep n. So this tells us we only need n. And when I say we only need, I mean we only need to look at. We only need to do analysis on this many, right? Because after that, the DFT is just going to repeat itself. So who cares? It'll repeat itself forever. We get all the information we want in these n, okay? But now, right, now add the fact. So now if we add the fact that, okay, x of a minus frequency k is the same as the conjugate of the positive frequency k, well, that tells us that we really only need to care about these n over 2. Why? Well, because if I want to know x of minus 1, well, I know that's the same as x of 1 conjugate. And I already have x of 1 because I'm caring about this part of it. Okay? So what we've done, right, okay, so I'm going to store these. If you want x of negative 2, well, big X of negative 2, well, I'll just take big X of 2 and I'll conjugate it. And boom, I give you your answer. Okay? So what I'm saying here is that from here, we're telling us that we only need n over 2 plus 1. In other words, the set of frequencies we really need to keep for real signals is this. It's a pretty important idea. Okay? It's very important because A, it halves our storage. Who cares about storing n? Well, now we can store n over 2, so it makes it easier for us, because a lot of the times in real life, our signals are real, duh. We don't really deal with actual complex valued signals, so this is a nice property to have. Okay, let's quickly run through the proof. So the proof, well, let's first write, so our goal is to show that x of minus k equals x conjugate of k. So whenever you have a proof, write out what this thing means. So remember, recall real quick, just recall here, that x of any k is equal to, well, that's the DFT, right? So that's the DFT, so the sum from n equals 0 to n minus 1 of x of n e to the minus j 2 pi kn over n, right? This right here is definition of the DFT. Okay, and then if I plug in minus k, well then I get x, so now I'm going to go back to my what I want to prove, right? I want to know what x of minus k comes out to. So I'm going to plug in minus k in here. I'm going to get the sum from n equals 0 to big N minus 1. Okay, now remember, my signal x is real. Because x is real, I'm going to use the property that x of n is the same as x conjugate of n. Fair? Because x is real. Okay, so I know this is true. So here I'm going to replace x of n with x conjugate of n. No problem, right? They're the exact same thing. So I haven't changed the expression. And I'm plugging in minus k here, so I'm going to replace k, so e to the minus j 2 pi. I'm plugging in minus k n over n. Okay. Notice that this whole thing can be written as the sum from n equals 0 to big N minus 1 of x conjugate of n. This guy right here is e to the minus j 2 pi k n over n, all conjugate. Because what does conjugating do? Remember, when you have a complex exponential, complex number, and you conjugate it, that means put a minus inside the exponent. So what have we done? If we wanted to go from here back to here, right, we would take this conjugate, that means put a minus here, so we get this. So these are equivalent. Great. Now what I'm going to do is another nice step. So I'm going to write underneath here that x of minus k equals, so now let's continue. So the sum from n equals 0 to big N minus 1 of, I can write, so there's a property, another property, and you can look and experiment with two complex numbers, just sanity check, but AB conjugate is the same as A conjugate, B conjugate. So from that, I can take this expression and I can write this as BOP, big thing, x of n, e to the minus j 2 pi k n over n, all conjugate. Wonderful. Okay, and now what am I doing here? I'm taking the sum of a bunch of conjugates, right? There's another property that nicely says that this conjugate can come entirely out of the sum. So I can take away this conjugate and take it out from just inside here, and now I can conjugate this whole thing. So I can sum everything up and then conjugate it as well, and we're equivalent. Okay, good so far? So now, well, what do you notice? Please tell me you looking at this and you recognize it. Well, this is the definition of the DFT from up here. So this right here is exactly x of k. So what you've shown is that this thing equals, well, inside I have x of k, and outside I'm conjugating it, so that's x conjugate of k. So boom, we've shown that this guy equals that guy. So we have shown the big property, the big famous property, that x of minus k equals x conjugate of k. Okay, very nice proof to know. It only works because the signals are real, which allowed us to sort of make this substitution. We just substituted x of n here with x conjugate. We could only do that because the signal is real. That's why this property only works when your signal in time is real, not imaginary. Okay, in the interest of time, okay, you know what? I'm just going to do it. It might be good, just to review. Okay, not to review, to learn. Second theorem is Parseval's theorem. Which says that the energy of my signal in time is the same as the energy of my signal in frequency. It's a lot of lines, my bad. Go away. Sorry, I don't have enough money to buy a pro subscription. So if you subscribe and leave some likes and comments and that stuff might help out, I would appreciate that. I'm kind of running on bare necessities, but it's okay. Okay, let's prove this. So we're saying that the energy in the time, I have my signal, I take its energy in time, I take its DFT, and then take its energy and frequency, I'm the same. This is very important for us because it means that our transform, the DFT, is not losing any energy somehow. Energy is still conserved, which makes it nice for analysis. So, do we really want to do this? Okay, I think I'm going to pause this because this is I've already done this proof 3 times in the last week in recitation and lab section and stuff. We're going to pause. But remember this theorem, okay? And the third theorem, important here, is I'll make a video proving it sometime later and post that after this video. The third property is linearity of the DFT. So this says, let my signal z equal alpha times x plus beta times y in time, okay? And let's say I know that the DFT of x is big X. So the DFT of big X, little x of n is big X of k. The DFT of little y of n is big Y of k. Then the DFT of z of n would be big Z of k. Well, I'm saying that big Z of k equals alpha times big X of k plus beta times big Y of k. A very simple idea, but it says that if my signal is like a combination of signals in time, then its DFT is a combination of those DFTs, scaled by the same coefficients. So the DFT is linear. This follows very straightforwardly from the proof. I'm not going to waste your time. No, we're not going to spend time on it. But yes, I believe one of the videos before, so that's it for DFTs. I think there was one video talking about cosines and sines. So hopefully, I think that video got filmed already. So hopefully we're done with DFTs and we can move on to Fourier transforms, which are a bit more interesting. So bye-bye. Nice, very nice doing this unit with all of you, and hopefully see you in the next unit. Goodbye.